that was more a function of the fact that lab and you're really comfortable. So trying to hold up Yep, it's always listed in Web of Science, electron charge to mass ratio. We'll have a review session, so it'll be separate next Tuesday. Yes, sir.
Thank you.
I know you may be Adam who does a lot more.
Yeah, that's why I thought you were doing the first.
Yeah, I know. I do it sometimes.
What do you do this weekend? What? Alex, birthday today.
Yeah, because like sometimes we miss too many.
Yeah, I didn't know if that was like what you guys did. That's what I was assuming, but.
Yes, I mean, if we had all the lab temporal periods in the world, we would of course do it every time, but it's always kind of.
Okay, thank you.
All right, so let's go ahead and get started. I think that I have a decent shot at getting through all of the theory for your homework, homework 8. I might have a little bit of cleanup to do on Wednesday just in terms of applications, but Wednesday's lecture is the cutoff for exam number 2 no matter what, because of course there is no lecture on Friday, okay? This week you have your electron charge to mass ratio lab. That's homework 8 material. It'll be well timed. And again, unfortunately, we're going to have to squeeze a little bit around the lab setups. This should be the only lab where we have to do that a little bit. And then hopefully you are looking into seeing if you are interested in getting free for the exam review session, which will be a week from tomorrow. So not at our normally scheduled class times. So any quick questions before we get started?
Honors projects, anything about that?
No, I don't want to get into that right now. I want to make sure we get through homework 8 stuff. Okay. Okay, so here we ended up at a super awkward spot. So basically this is exactly what I had on the board at the end of last time. Let me recap. We have a magnetic field in the region which is pointing straight downward. It's uniform. And then in order to get all the interesting stuff into the plane of the page, we need to take our current loop and we need to look at it from the edge view. So current coming toward you, going across, going in, and then the fourth side, by definition, you can't really show it because it's in the back. And what we did was, we found that the most relevant forces, the ones that cause torque, are now in the plane of the page. There are, of course, forces on the other two sides, the front and back as well, but they don't actually cause any torque. I went ahead and did the slap rule with the currents, the out current and the in current. If you do the slap rule with the magnetic field, you'll get these forces. Very clearly, those forces cancel, so the center of mass doesn't move, but they both actually cause clockwise torque. So this thing will experience a clockwise torque. And if we do the fancy pants way, instead of saying clockwise, we say minus k hat, okay? Right here, you can see that the torque is maximum because you can see that these forces are entirely tangential. These forces are applied completely along this circle. So that is the optimum orientation of cause force. As Jacob just demonstrated, if you open a door, you push like that, okay? Or pull like that. Now, as this loop rotates, these forces actually don't change direction because these currents actually don't change direction. Even if, as this loop rotates, the out current and the in current stay that way. And so these forces continue to be in the same direction. So we just copy them here, 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 okay? And what you can see is that unlike how you would open a revolving door, these forces are starting to fall off the tangential path. And so here, while the torque is still clockwise, it's going to be less. These forces are not now along the circle entirely. There's a component of them that's going to waste radially. Until we get to this orientation, where these forces are entirely radial, and now the torque has become 0. Okay, so that's the least torque you can have. what's happening at this moment is that these two forces are trying to pull directly outward from the pivot, so no torque. And then we find if I were to release it here from rest, it would just stay there because it experiences no torque. But if I release it from over here and I let it rotate, by the time it gets here, it's built up angular velocity, so it's not going to just stop. So it's going to overshoot. But we find that if it overshoots, then the torque actually reverses and brings it back the other way. So that's counterclockwise, or plus k hat. So this seems to be highly suggestive that there's an equilibrium orientation, and that is this. So if you are not in that, you will rotate either clockwise or counterclockwise to get back to this, okay? So before we do anything else, I want to get rid of all this clutter. This is way too much drawing to do, so what I want to do is come up with a shorthand way to do all this. I'm going to take this current loop that I have, and I'm going to define something called the normal vector. So that goes like this. This is a second right-hand rule. You take your right hand, you wrap your fingers in the direction that the current is actually circulating, like this, and your thumb gives a vector that is perpendicular to that plane. Now this isn't the first time we've done this in terms of we've defined a normal that we could use Gauss's law, right? Only in this case, there's a difference. So in Gauss's law, we just had a surface, and when we had an open surface, which by the way we never used for Gauss's law it was a closed surface, right? That made it easier because there's a normal defined by convention, outward facing normal. But if you had an open surface, there was an ambiguity in how to choose the normal vector, okay? So you could pick it either way, and hopefully remember that the only difference that makes is that the sign of the flux is positive with one choice and negative with the other, but it's the same amount, right? Well, now what we have is a current loop. So it gives us something to hang our hats on to choose one normal versus the other. So by the right-hand rule, what you do is you wrap your fingers around the current, and the normal is understood to go this way. So your right-hand rule, I'll call it right-hand rule number 2. So the right-hand rule that we talked about already was called the slap rule. So you slap one vector into another vector to get a third vector. That's the hard one. Right-hand rule number 2 is actually easy. I call it the Curly-Straighty rule. Okay? There's only 2 things involved. I'll try to draw it here. Okay? That's about as good of a drawing as I get. You can see I didn't go into cartooning. Okay? So that's a right hand. And it involves one thing that goes with your fingers and one thing that goes with your thumb. And your thumb is perpendicular to your fingers. Now, I call it the Curly-Straighty because we'll have lots of applications for this. This is just the first one. But you wrap your fingers around whatever is going around, and your thumb points straight, and it's going to be perpendicular to the entire plane. So in my case, the fingers get the current, that's the curling thing, and your thumb gives the normal vector. So that's why we choose this and not this, because that doesn't obey the right-hand rule. So now we don't have any ambiguity left, okay? So again, if you look at this, you can see that I've done this, right? I wrap my fingers around the current direction. My thumb gives the normal vector and is perpendicular to the entire plane that the current is circulating in. Now, what's pointing this way? Nothing. Nothing is actually physically pointing this way. Don't confuse this with a normal force. It has nothing to do with a normal force. Normal is just a word for perpendicular. Okay? When you hear perpendicular in math class, you don't think force, right? It's just a vector, and here's the purpose of it. It is an amazing shortcut, because with a single arrow, so I have three-dimensional space here, and with a single arrow, I can specify all this information. So if I tell you the normal vector points like this, that means that current is circulating in this plane, going this way and not this way. So with a single arrow, you can convey all of this information. So it tells you what plane in 3D space there's current and which way in that plane is it circulating. That's a lot of information from a single arrow. That's what it's for. Does that make sense?
Mm-hmm.
Okay, so you basically just have to imagine this. So every current loop carries around with it an arrow which is designed as a shortcut or mnemonic for how that current is flowing in 3D space. I'm going to go ahead and just mark it in my diagram. Here is my diagram of this current loop with the normal vector. So looks like that. Remember, it's perpendicular to the entire plane of the loop. I'll draw it in here like this. I'll draw it in here like this. And I'll draw it in here like this. And if I understand that that's my shortcut, all I have to do is draw that single arrow and not all the rest of this stuff, okay? So I'm going to redraw what I have. In fact, I'm going to go ahead and draw the magnetic field in a little more detail. And let me sketch in a summary of all this stuff that I just wrote much more compactly. I guess let me label these. This I'll call A, B, C, D, just so you're clear which one is which. So I'll go over here. This is A. This is B. This is C. And this is D. Something like that. Those are my normal vectors. So what we know is that the torque is maximum here. The torque is 0 here. And it is going to be some intermediate value at the other two, B and D. So what's going to happen if I release this? If I released it here, it would experience no torque and it would just sit there. But if I released it here, it would experience torque this way. So we can say that the torque here is clockwise, or minus k hat. And then over here, the torque will be counterclockwise, or plus k hat. And so what's going to happen, if I release it at A, let's say, it's going to speed up as it gets towards C, and at C, it's not going to stop dead, because even if the torque is 0, it's built up all this speed, so it's going to overshoot, go to the other side, but then it's going to get pulled back, because the torque is against it. So what's going to happen to this thing is it's just going to kind of go back and forth, right?
Pendulum.
What does this thing look like?
Pendulum.
It's a pendulum, okay? So that's exactly the analogy. It is an exact analogy. So if you understand how a pendulum behaves, you understand how a current loop behaves in a uniform field. Okay? Does that make sense?
Mm-hmm.
So the only difference is that a pendulum, of course, the equilibrium is always down, right? It's always at the lowest point. Yes? This is a known thing. You don't need to have taken physics 270 to know that, right? So pendulum oscillates around the bottom. Okay. Well, that's of course because gravity always pulls down, right? And of course, I pointed the magnetic field down because I wanted it to look exactly like that, right? But of course, if the magnetic field pointed that way, then the pendulum would be like a sideways pendulum, right? So the equilibrium of a pendulum, in this case, is that the normal vector is aligned with the magnetic field, okay? That's orientation C, that's your equilibrium. So you don't have to have this always quote unquote go downward, right? You can point the magnetic field in any old which direction. You can point it in some weird diagonal way, but then if you release a current loop in a magnetic field, it's going to oscillate around that, okay? Does that make sense?
You're gonna release a magnetic.
So,
What the fuck?
let's go ahead and work out the details. How much torque do you experience exactly? So we have sort of said that you do experience torque. We need an exact number. So let's go work it out. Now, if I'm going to work out the general equation, I obviously don't want to go to a special case, right? I don't want to go to this case because this case happens to be the maximum torque, right? That's, by the way, the same as a pendulum, right? A pendulum in this orientation experiences maximum torque because the gravity force happens to be entirely tangential, right?
Yes, sir.
Okay, so that is the maximum torque case for a pendulum. Let me not use the green because it's looking pretty faded. And then here, a pendulum experiences zero torque because, of course, at that moment, the force of gravity is just pulling radially outward from the hinge, right? The problem is that gravity always pulls down no matter what orientation the pendulum is in, okay? So I don't want to use a special case. I don't want to use the maximum torque case. I don't want to use the minimum torque case. Just like if I were trying to compute the gravitational torque on a pendulum, I want to use some case in between. That way I can get a general sense of what's the torque. So for instance, if I was at an angle theta, this is just physics 1 calculation, if I was at an angle theta, I would have a torque that's somewhere in between the maximum and the minimum, right? And what I would do, just to remind you how to compute torque, to get the magnitude of the torque, you use this equation. You remember this from physics 1?
Mm-hmm.
Okay, I know it's a vector, but I'm just working with the magnitude right now. You need to put in the force, you need to put in the leverage, that's R, yes? Distance of the force acts from the pivot. And then sine of theta, you take, and I mean there's a million ways to do this, I don't remember which one Adam does, but the way I get theta is I draw a radial line out from the pivot through the force application point, and I measure this angle. So this, I get, it's the angle between a radial line and the force vector. Is this how Adam does it?
No.
No?
No, but
I've seen it as r hat, comma, force.
R hat?
vector. R hat is the radial line you can do.
Oh, okay. Oh, so you're saying just define a vector like this, R hat,
Yeah.
point radially outward. It's basically the same thing, right?
Yeah.
So yeah, there's a million different ways, but if whatever floats your boat, any method is right if it identifies the correct angle, right? So I want to do it for my particular situation. I probably should redraw this because this is going to get messy. So let me draw it for my situation. So here is my current loop, and I'm going to put these guys one more time before I completely move away to the normal vector notation, there is my relevant currents. And then my forces look like this. Like so. I should tell you that this loop that I'm using is going to have dimensions of L1 and L2. So I'm going to assume it's a rectangular loop, just like this one, okay? And then I have to tell you which is the side we're looking at. Let's say we're looking at side, let's say we're looking edge on at L2. It doesn't really matter. So this is L2. All right, so let's work it out. Let's work out what is the torque. Well, first, the pivot, of course, is going to be somewhere right in the middle of the loop, okay? The center of mass. It's not on the front side, it's behind the front side, but, right, I'm trying to show the center of mass. It's not here, it's here, right? That's the rotation point. Does that make sense? Okay, so let's do it. I'll draw a radial line out from the pivot through the force application point. There's my theta. So let's work out the torque. The torque is, first of all, how much leverage is this? How much distance is that?
Half.
Half of L2. The force itself, and then sine of whatever that angle is, okay? Let me fill in the force. The force is a magnetic force, yes?
Yes, sir.
Okay, so let me remind you of the magnetic force formula on a piece of straight current, ILV sine of theta, between I and B. Talked about that last time.
Mm-hmm.
Current's easy. There's one current that circulates around the entire loop. Which L is this? It's this length, right? L1
Should
or
be
L2?
L1.
It's L1, okay? So we get I times L1 times B, and then we have another sign. We got stacked signs here. We got sine and a sine, but this one's easy. Because what's the angle between this current
And the
and the magnetic field?
90.
90. Is it 90 all the time? Is that a general statement? Is this current always 90 degrees to the magnetic field?
Yeah.
Yes, it is. Awesome. Get rid of that sign permanently. Okay? So, sine of 90 all during rotation. And I'll just leave it times 1. Okay? So that's the torque due to just one of those forces, but there's another force. What do I do to account for both torques?
Add them.
Multiply by 2.
Oh.
Exactly. They're exactly the same. They both want to rotate
In the same
the
direction.
same direction. So multiply by 2 for account for both forces. Okay, so let's see what I wind up with. This 2 cancels with this 2. And then I will get I'll group L1 and L2 together because they're buddies. They're both lengths. Sine of theta. And I'm pretty much done. I just want to put a few bells and whistles on it. What's the quantity L1 times L2?
Area?
It's the area of the loop. And the theta, you might ask, do you need to calculate that theta in that awful way that you need to compute angles for torques? No, you don't. Because it turns out that that theta is exactly the same as the orientation, or as the angle between the normal vector and the magnetic field. can convince yourself of that, because that's far easier to identify. To give you an example, what's the angle between the normal vector and magnetic field in case A? 90. What's sine of 90? 1. Maximum torque. Just like we already saw when we were looking at the individual forces. What's the angle between the normal vector and magnetic field in this case?
0.
0. What's sine of 0? 0. 0 torque. So, if you don't believe me, that this theta that we got for the torque is the same as this angle, hopefully now you're more convinced. So, we're pretty much done. The only thing I want to do is just put in a few bells and whistles, the first of which is that oftentimes we don't want to do this with just one current loop, we want to have a whole stack of them.
Awesome.
The reason why is if you have not just one current loop, but you have 1,000 loops, if they all experience the same torque, then you get 1,000 times the torque on them, right? So it's very common in these applications is that we don't want to deal with just one, we want to deal with a whole bunch. In fact, I think on one of your homework problems, there's even an N that sneaks in there. Because you don't just have one current flowing, you have a whole stack of them flowing in the same direction. It's a general case that in order to increase these forces and torques, you might not just want to use one straight segment or one current loop, you want to just use a bunch. The only reason I'm introducing N now is because for current loops, we are going to do this almost all the time, okay? Question?
What if the current loop is circle? It's a circle.
Yes, and so that's the other thing. You might question what would happen if this was not a rectangle. What if it was a circle or some other bizarre shape? It turns out that this actually still works. You just put in the area.
2 pi r.
So I use a rectangle as a means to an end because it, of course, has nice, clearly broken down sides. But if this is a thing that works for any area. So if you have a circular current loop, just put in pi r squared for the area. It's good to go. I know I didn't rigorously prove that, but I'm telling you it works. If you work out all the calculus, because a circle doesn't really have clear sides, right? You would get this. So, the final thing I want to do, let me go over here. Need to create myself some space. Where do I want to go? I guess I'll sneak over here. So let me copy down my formula. NIAB sine of theta what I want to do is I want to create myself a bundle. I want to create myself a bundle of all the properties of this entire current loop, okay? So that includes what is the current in it, what is its area, and how is it oriented in space? So that normal vector, those are all properties of this current loop, right? So I want to bundle everything together. Oh, and the number of turns as well. N, I, A, and the orientation, this is defined as what's called the magnetic dipole vector. It's all the properties of the current loop that you need to know. So it's the properties of the current loop, all bundled together. This part here doesn't normally change. These are fixed. So once you know the number of loops, the current going around them, and the area of them, that doesn't change, but of course the orientation may change. So that may change if, of course, the loop experiences a torque, because the normal vector wants to align with the field. So the units of this thing, oh, by the way, the triple equal sign is, if you haven't seen it before, that is defined as, okay? That's how It's not just equal, that is the definition of a magnetic dipole vector. So the units of this thing, well, n is just the number, n hat is just the unit vector, so the units will be the units of current times area. So that'll be amps square meters. Question?
Are you saying that this is the property of that when they have a dynamo that is using magnetic field, this is what they give you?
I haven't talked about most of those things yet, so I think that's a little bit getting ahead of ourselves.
Okay.
So, if we do that, then I have taken these three things and just created a definition for this. So I'm going to write this as mb sine of theta. And then what I note is that the direction n hat is the same as the direction of this. So they have the same direction. I've just literally made the normal vector a part of a bigger vector. Those multipliers in the front are never negative, so there's no way that the dipole vector couldn't be any point in any other direction besides the normal vector. In fact, all I've done is incorporated the normal vector into a bigger construct. So here I have it. Instead of writing n, I'll just write m. So with this, we are done compactifying this into as small a space as possible.
What's the triple equal sign again?
Defined as. So we're defining it in this way. So we are ready to write down the magnetic torque on a current loop. The size of this torque is mb sine of theta between them, where, just as a side note, we might want to include what is m, and the direction is such that m wants to align with b. That's it. So we just look at a particular situation, right? We see that here, the magnetic dipole is not aligned with B. But how can it most directly align with B? By going clockwise. So the torque is clockwise, or minus k hat. Over here, the dipole vector is not aligned with B. How can it most directly get that way? By experiencing counterclockwise torque. Okay? M wants to align with B. Question?
Could you also write that as tau is n cross b?
Yes, next thing I was going to do. So for those of you that are familiar enough with the cross product, you can compactify all of this into a cross product again. Now, let me show you that. That's why I brought this thing along here with me. So you can imagine it like this, okay? Here I have my dipole vector right here. Here I have the magnetic field, okay? Now if I release it like this and this is not aligned with this, it'll experience a torque until it is. So this will just want to say, hey, oh, I want to align over there, ow, okay? So, right, so I want to, this most directly wants to align with this, right? It'll experience a torque. If it's over here, it'll experience, if it's over here, it'll experience a torque like this, right? So really, obviously the rotation axis is going to be perpendicular to those, right? In fact, I had to put this thing here to allow this to most directly rotate like this. Well, this is the direction of the torque, which really just says that M wants to align with B, right? So M wants to go over there because M likes to align with the magnetic field, so the torque is this way, which really, remember, there's nothing actually rotating this way. That's indicating a rotation like this, right? So if that makes sense to you because you are accustomed to the cross product, that's great. If not, don't worry about it, okay? Just remember that this likes to align with this. So whichever direction this can most directly align with this, that's the way it'll actually torque. So this wants to torque over here. If it overshoots, it'll want to torque back. So it kind of goes like this, right? Does that make sense? Like a pendulum.
I see.
Questions?
Yeah, why is the torque going up again?
So remember that if the torque is, if this wants to torque with this, we don't say clockwise, we say minus k hat, right? That's just a fancy way of saying it. That's just rotation axis enhanced. So if this wants to align with this, the rotation axis is like that, right? So again, if you're not fully comfortable with the advanced way of giving the torque, just identify it as, so if this wants to align with this, then it's clockwise, that's minus k hat, right? If this wants to align with this, we would say counterclockwise or plus k hat, right? So again, if this is comfortable for you, great. If this is informative for you, great, but not everyone has seen this. So this is just the same thing, just requiring you to just do it in pieces, okay? So this right here is, you just take M, the magnitude of M, the size of M, the size of B. So this is, remember, all the properties of the loop are bundled in with M. The only thing left, of course, is the magnetic field, which is what it's reacting to. You can't bundle that in with it, right? So you want all the properties of the loop. You want the field it experiences, and then the sine of theta is going to determine whether or not your torque is maximum, like this, it's minimum, 0, or it's somewhere in between. And the direction of the torque is such that M always wants to align most directly with B, okay? So that's the equilibrium of this quote-unquote pendulum. Question?
So we've been using right-hand rule for like find the force direction and then find the normal vector, and now we find it through the torque too?
That's right, 3 right-hand rules.
Jesus.
That's why this one, this is just an easy thing to remember, so that you don't have to do a 3rd right-hand rule. So, and I also should point out that the right-hand rule for slapping I into B, that's already done here. It's actually incorporated into this, okay? So you don't actually need to do that anymore. It's basically gotten incorporated into this. So you would never end up doing, usually, that, because it's just, we want to fold it into something new, right? Because, you know, if you're starting from like what we just did here, this is a lot of work to do, right? This is, have to find the forces, then get their leverage and their thetas and all this business. That's the whole reason why we wanted to do this, is that we have something that we can just use for a current loop. It's ready off the shelf, right? Let's go ahead and plot the magnitude of the torque versus theta. So remember that the maximum angle that two vectors can make to each other is 180. So really, we don't need to draw any angles other than between those two. And since it's a sine function, it looks like that. The maximum torque occurs, as we mentioned already, at 90 degrees. And that maximum amount of torque is mb. mb sine of 90 is just mb. But we really have only focused on angles from 0 to 90, so it's definitely worthwhile taking a brief look at what happens with angles bigger than 90. Now, if I released a pendulum from here, it of course would still swing down, right? Yes? So if I released it from here, it would still swing down like that, right? It would still experience a clockwise torque. Likewise, if I release something from over here, it would still want to go counterclockwise. It's just that the torque isn't as much as it is at 90 degrees. But we do wind up with a weird case. This case, I guess I'll call that E. What happens if I have a pendulum that's not like, let me use this. So we know that pendulums swing like this, right? But what if I had a pendulum where I released it right here? Is that zero torque?
Yeah.
Yeah, I could get it to balance just like that. Of course, any little thing is going to knock it down. So there is an equilibrium up there where you experience no torque also. The difference is in the type of equilibrium. So this is a stable equilibrium because if you perturb that a little bit, it'll just come back. But what we call this is an unstable equilibrium. Because if you knock it one way or the other, it's not coming back. It's swinging all the way to the bottom. Okay? Now, if you don't believe me that this could happen with a current loop, remember what we found was that when it's in this orientation with the, let's do it with the, let's put the normal vector back here. When it says in this orientation, the forces are outward. So try to give that a little bit of a twist and we'll see what happens. Like this way or this way, like a pendulum. Like that or like that. Okay? So give it a twist. Try it the other way. Forces that are outward, flip it, or tend to bring it back, right? Okay? Let's try it the other way. Here, I'm going to take this off because it might hurt somebody. Okay? So here the forces are inward, like this. Okay? So that's stable. Okay? But try to give it a twist one way or the other. Okay? So notice it doesn't go back. So that's what happens with a current loop in that orientation.
Oh, so you mean if it's released on top, it's never gonna go back again to the top?
That's right.
Okay.
So basically, I like to think of this one just like a pendulum. The reason it has zero torque is because it's paralyzed by indecision. Okay, it can't decide how it wants to get down here. It wants to get down here, but it can't decide, should I go this way or should I go this way? So you need to give it a little push one way or the other. Okay, and then make the decision for it. Okay, so that's the torque on a current loop. Okay.
Is there an angle that it won't, like once you release it, it won't go back to it again?
It's just like a pendulum, right?
Yeah,
So
pendulum.
whatever angle you release it at rest, it'll return to the other
Totally.
side. So if I released it here, it would swing back and forth between these two orientations and it'd have its maximum speed on the bottom. In fact, that brings me to my next point. Let's work out the energy, right? Anything we can do with force or torque, we can do with energy. In the interest of time, I'm not going to do the whole rigmarole, but I'm just going to tell you roughly how I got this. So you guys, of course, know good old work formula, right? And then we can say that if you have a conservative force, we can store potential energy, right? Now you can do the same thing with torque. You just do the angular version of that. So force goes to torque, ds goes to d theta, and of course you can store potential energy. We always have to pick a reference where u equals 0, that's true regardless. And let me skip it's like 2 lines of math, but in the interest of time, let me skip it. I'll put this in here. An integral of sine is what? Something, something cosine, right? Negative cosine, is that right? Okay. So I'm going to get something, something cosine. In fact, what I get is this, where I should tell you for full disclosure, u equals 0 is set at a kind of an odd place. It's set where the theta is 90. And by the way, if this looks suspiciously like a dot product, it is. Right, that's the classic dot product, right? You got two vectors going in, one scalar leaves. And the scalar is bigger or smaller depending on the cosine of the angle between them, right? Is this something comfortable? So, let's take a look at what this equation tells us. If we have a magnetic field like this, if your dipole points like this, the potential energy, ironically, is 0. That is neither the lowest nor the highest potential energy. The minimum potential energy, as you can probably guess, is at the bottom, right? That's just like a pendulum, right? It's at the lowest point. The minimum will be minus mv cosine of 0, which is 1. So that's the lowest potential energy. And then over here, this will be the maximum potential energy, which is going to be plus mv. Cosine of 180, so that's going to produce that. If you wanted to sketch this function, what does the potential energy look like from 0 to 180? It looks like a negative cosine, with 90 being the midpoint. It's not the lowest nor the highest potential energy. The lowest, which is the state that this seeks, is minus mv, and the highest is over here. Now you think it's weird to set the potential energy to 0 in the middle. Let me try to convince you that that would have been a really smart move with the pendulum too. We never did it, but it would have been pretty awesome. So if we have a pendulum like this, and we compare these 3 points on a pendulum, in physics 1, you probably set this as h equals 0, right? And so my potential energy here would have been 0. And then the length of the pendulum here, when you're at this point, you'd use mgh. What's the height there? How high is the pendulum up?
L.
L. And then over here, you would have used mg times, what's the height here? 2L. Which, that's fine. The potential energy is 0 at the lowest point. But let's choose a different one. How about we choose h equals 0 in the middle? So then, the energy here is 0. What's the energy up here? mg times what's the height above there?
Max and
L. So plus mgl, and then here,
negative.
negative mgl. I like that because if you can get over the fact that negative potential energies are lower than 0, which you should have long by now, it's much more symmetric, right? So we set the 0 in the middle. Any positive values are higher, any negative values are lower. In fact, you can tell exactly where a pendulum would then be by looking at the sign of the potential energy, seeing if it's positive or negative. If it's positive, it's somewhere up here, and if it's negative, it's somewhere more down here. That's exactly what we've done over here. So positive angles, if you're over here somewhere, the angle between the dipole vector and the field is somewhere between 90 and 180, and if your value is negative, you're somewhere between 0 and 90. Okay. So that actually gets us all the theory of what you would need for your homework 8 in exam 2. But what I'm going to devote Wednesday to is a whole bunch of applications to all this stuff. We'll talk about electric motors. We'll talk about making nuclear weapons. I forget what else. On Wednesday morning, we'll do a bunch of applications. Some that are on your homework, some that are not. We'll pick that up